Welcome friends. In this module we discuss simplex method. The simplex method is an iterative procedure for solving a linear programming problem in a finite number of steps. This method provides an algorithm which consists in moving from one vertex of the set of feasible solution SF to another in a prescribed manner such that the value of the objective function f of x at the succeeding vertex is greater than that of the preceding vertex for a maximization problem. The algebraic procedure of solving a linear programming problem through simplex method is at first illustrated through an example. In this example, we are considering maximize f of x that is equal to 4x1 plus 5x2 subject to x1 minus 2x2 less than or equal to 2, 2x1 plus x2 less than or equal to 6, x1 plus 2x2 less than or equal to 5, minus x1 plus x2 less than or equal to 2, where x1 greater than or equal to 0, x2 greater than or equal to 0. The constraints are x1 minus 2x2 less than or equal to 2, 2x1 plus x2 less than or equal to 6, x1 plus 2x2 less than or equal to 5, minus x1 plus x2 less than or equal to 2, and finally x1 the non-negativity condition x1 greater than or equal to 0, x2 greater than or equal to 0. So, we are solving this problem step by step using the method of using simplex method. So, in step 1 we are adding slack variables to the constraint inequalities and state problem in the general form as follows. That means, maximize f of x equal to 4x1 plus 5x2 subject to x1 minus 2x2 plus, we are assuming the slack variable x3 equal to 2, next 2x1 plus x2 plus x4 equal to 6, x1 plus 2x2 plus x5 equal to 5, minus x1 plus x2 plus x6 equal to 2, where x1, x2, x3, x4, x5 and x6 are greater than or equal to 0. Here x1, x3, x4, x5 and x6 are the slack variable considered. So, this is the first step. In the next step, here since the problem is with 4 constraint equations in 6 unknowns, to get an initial basic feasible solution, the variable x3, x4, x5 and x6 which are having linearly independent column vectors are taken as basic variables, and the other 2 variables x1 and x2 are equating to 0. When we are writing it in the matrix form, this will be like 1 minus 2 1 0 0 x1 x2 x3 x4 x5 x6, then 1 2 sorry in the second is it is coefficients are 2 1, then x3 0 x4 1 0 0, then in the third equation 1 2 0 0 1 0, and in the last constraint equation it is minus 1 1 0 0 0 1 into x1 x2 x3 x4 x5 x6, that is equal to 2 6 5 2. It is just like this. So, here the column vectors of x3, x4, x5 and x6, they are linearly independent. So, we are considering these two, these 4 variables are considered, and these 4 equations are here. So, we can consider 4 variables and 2 variables x1 and x2 are assumed as 0. Then, when we are equating x1 and x2 as 0, we are getting a solution 0, x1 0, x2 0. Then, solving these constrained equations, we are getting x3 equal to 2, x4 equal to 6, x5 equal to 5 and x6 equal to 2. So, we are getting a solution that is 0, 0, 2, 6, 5, 2. For this value, our f of x, the value of f of x is 4 into 0 plus 5 into 0 plus 0 into x3 plus 0 into x4 etc. Finally, we are getting f of x is equal to 0. It is to test whether the current solution is optimal or not. So, this is a basic solution and it is basic feasible greater than or equal to 0. So, basic feasible solution, and we do not know whether it is the optimal solution, that means whether this solution maximize our f of x. For this solution, the value of f of x is equal to 0. So, next is it is to test whether the current solution is optimal or not. For this, we start with the simplex table and calculate the quantities. It is called Zj minus Cj. It is called known as net evaluation. Net evaluation for each of the variable xj. So, a specimen of simplex table which conveniently displays the basic feasible solution xb, the associated cost vector cb, basic this is the xb that is displays the basic feasible solution, and cb, that is associated cost vector, the basic vector yb, and the column vectors yj's corresponds to the coefficient of the xj's in the constraint equations for all j, and the net evaluation zj minus cj's for all the variables are shown as, it's just like it will be like this. Here means Cj values are here, then C1, C2 etc. Cn values are here, then corresponding column vectors y1, y2 etc. yn are listed here, then xb, yb and cb are here, cb, yb and xb. These values are this is the model of a simplex table. Then for the incoming variable xr, we are considering some ratio xb1 divided by y xb1 divided by y1r for y1r greater than 0. Okay, we can see what is happening in this problem. Then we can get an idea about what is the table intending. So, here when we are considering this problem, here we are getting here our basic cost associated with our basic variables 0, 0, 0, 0, because our objective function is 0 x3 plus 0 x4 plus 0 x5 plus 0 x6, and the corresponding variables are x3, x4, x5 and x6. The value taken by this or value assigned for these variables after substituting the other variables as 0, they are 2, 6, 5, 2. These are listed here. Then the cost in the coefficient matrix, that is 1, 2, 1 minus 1 minus 2 1 2 1 1 0 0 0 0 1 0 0 0 0 0 1 sorry 0 0 1 0 0 0 0 1. So, this is for y1, y2, y3, y4, y5, y6. So, based on these values, the value of f of x is equal to 2 into 0 plus 6 into 0 plus 5 into 0 plus 2 into 0, that is f of x is equal to 0. So, we can mark the basic feasible solution that we obtained after substituting x1 and x2 as 0 and after considering x3, x4, x5 and x6 as the basic variable. The value of f of x is 0. It is listed in the table like this. Here in this table, the cost associated with the given variables, that is x1 4, x2 5, x3 0 0 0 and 0. Now, to test whether this f of x is optimal, f of x equal to 0, that is this solution is optimal solution or not, we are calculating Cj minus Zj. Cj minus or Zj minus Cj, Zj minus Cj values are calculated, Zj minus Cj values are calculated. So, C1 is 4, C2 is 5, C3, C4, C5 and C6 are zeros. So, it is Zj value calculated as this 1 is multiplied with 0, 1 into 0 plus 2 into 0 plus 1 into 0 plus minus 1 into 0, finally 0, 0 minus 4, that is minus 4. The next is minus 2 into 0 plus 1 into 0 plus 2 into 0 plus 1 into 0, again 0 minus 5, that is minus 5. Then 1 into 2, 1 into 0, 0 into 0, again this is 0, here all the values are getting as zeros. If all the Zj minus Cj values are greater than or equal to 0, we can conclude the solution is an optimal solution. All Zj minus Cj's are greater than or equal to 0, but that is not the case here. For Z1 minus C1 and Z2 minus C2 are negative values. Among these, Z2 minus C2 is the most negative. So, we are decided to consider x2 as a basic variable, but we can admit only 4 basic variables. When we are admitting x2 as one of the basic variable, we want to remove one of the basic variable for x3, x4, x5, x6 from the basis. So, to decide the variable, we are considering the ratio, that is minus 2 divided by minus 2, that is this 2 divided by minus 2, then 6 divided by this value 1, 5 divided by 2, then 2 divided by 1. So, among these the minimum positive is identified. So, it is negative, here 6, it is 2.5, it is 2. The minimum positive is 2 divided by 1, that is equal to 2. So, here this minimum positive is for the last row, that is for the basic variable x6, and incoming variable is x2. So, the common element for these two, that is this one. So, this one is called the pivotal element. So, we are keeping this pivotal element here and we want to make all other elements of this column as zeros by some linear transformation. So, for that we want to transform all the rows so as these variables are becoming zeros, that is in the next step. So, for that this R1 changed as R1 plus 2 into R4. When R1, the first row is added to 2 times the last row, minus 2 plus 2 into 1, that is 2, this will become 0. Now, here we are getting the new table as the cost values 4, 5, 0, 0, 0 and 0, and our basic variables x3, x4, x5, and instead of x6, x2 comes here. Now, we are making the change for the first row, that is R1 becomes R1 plus 2 into R4. So, this will become 2 plus, that is the value of x3, it was 2, 2 plus 2 into 2, this will become 6, 2 plus 4, 6. Then the value here in the fourth row, the value is minus 1. So, our change is first R1 plus 2 times R4, that is 1 plus 2 into minus 1, that is 1 plus minus 2, that is minus 1 becomes here. Then next is minus 2 plus 2 into 1, that is minus 2 plus 1, it will become 0. Then 1 plus 2 into 0, that is 1, 0 plus 2 into 0, again 0, 0 plus 2 into 0, 0, 0 plus 2 into 1, that is becoming 2. Next, we want to change the next element of the second the column, that is this one, change this 1 to 0. So, for that we are making a change for R2 as R2 implies R2 minus R4. Now, R2 changes, that is the value of x6 changes, 6 minus 2, that is 4, then 2 minus 1, that is 3, 1 minus 1, 0, 0 minus 0, 0, 1 minus 0, 1, 0 minus 0, 0, 0 minus 1, minus 1. And to change the other element of the second column, that is this 2 to become 0, we can make a change, that is R3 as R3 minus 2 times R4. So, this implies the value of x5 changes as 5 minus 2 times 2, that is 5 minus 4, that is becoming 1, then 1 minus 2 times minus 1, that is 1 minus 2, that is 1 plus 2, that is becoming 3, then 2 minus 2 times 1, 2 minus 2, 0, 0 minus 2 times 0, that is 0, 0 minus 2 times 0, again 0, 1 minus 2 times 0, 1, 0 minus 2 times 0, that is 2 times 1, that is minus 2. And the value of x2, that is just like 2, then the other elements minus 1, 1, 0, 0, 0, 1, no other change. Now, our solution changed to x6 as changed like this, x1 is 0, but x2 is 2, x3 is 6, x4 4, x5 1 and x6 is 0. Now, the basic variables are x3, x4, x5 and x2. Corresponding to this solution, the f of x value, that is equal to the associated cost x3 0, x4 0, x5 0, cost of x2 is 5. So, associated with this solution, the objective function is 6 into 0 plus 4 into 0 plus 1 into 0 plus 5 into 2, that is 10. So, earlier it was 0, now it is jumped to 10 because of this new solution. Again, we want to check whether the new solution is an optimal solution or not. Again, we are calculating Zj minus Cj values. So, here first Z1 minus C1 value, that is Zj is calculated minus 1 into 0 plus 3 into 0 plus 3 into 0, then minus 5, minus 1 into 5, that is minus 5, minus 5 minus 4, we are getting it as minus 9 here. Next is 0 into 0 plus 0 into 0, 0 into 0, 1 into 5, 5 minus 5, that is 0. And here 1 into 0, 0 into 0, 0 into 0, 0 into 5, minus 0, that is 0. Next 0 into 0, 1 into 0, 0 into 0, 0 into 5, again 0 minus 0, again 0. Here it is 0, 0, 1 into 0, 0, 0 into 5, 0, minus 0, that is 0. 2 into 0, minus 1 into 0, minus 2 into 0, but here 1 into 5, that is 5 minus 0, it is 5. So, we are getting the net evaluation like minus 9, 0, 0, 0, 0 and 5. Again the optimal condition is not satisfied because all the Zj minus Cj values are not greater than or equal to 0. Here 1 is minus 9. This corresponds to the variable x1. So, our variable x1 has to come as the basic variable. So, x1 is an eligible variable to become a basic variable. Now, if x1 comes to the basis, one of the variable from basis has to be gone out. That is to be decided. For that, we are finding the ratio. That is here, as before it was minus 2 divided by 2 divided by minus 2, 6 divided by 1, 5 divided by 2, 2 divided by 1. Similarly, here 6 divided by minus 1. 4 divided by 3, 1 divided by 3, 2 divided by minus 1. So, among this the least positive, that is 1 by 3. So, that is for the variable x5. So, x5 has to go out and x1 comes in. Then the new Simplex table will become so, here the basic feasible solution again changes. So, the new table, it is before the pivotal element. This is the element coming in, this is the variable coming in x1 and x5 goes out. So, the common for these two, that is 3. So, 3 is the pivotal element. So, our first step is to make the pivotal element as 1. For that, you want to divide this third row by 3. So, this will becomes or this becomes the cost 4, 5, 0, 0, 0, 0 and the basic variables x3, x4. Now, x5 goes out, but comes x1, then x2 is here. Where cost 0, 0, the cost of x1 is 4, x2 is 5. Then we are dividing the third row by 3, then this will the value will become 1 by 3, then the first element 3 divided by 3 1, 0 divided by 0 3 0, 0 by 3 0, again 0 by 3 0, 1 by 3, then minus 2 by 3. Now, we want to make all other elements of the first column as 0 by some transformation. So, to make such a change, the first element of this column, that is minus 1. So, the R1 changed as R1 plus R3. When we are adding R1 and R3, minus 1 plus 1, this will become 0 and the value, that is 6 is the value of x3, 6 plus 1 by 3. Here it is become 6 plus 1 by 3, that is 19 divided by 3. Then other elements, that is 0 plus 0 is 0, 1 plus 0, 1, 0 plus 0, 0, then 0 plus 1 by 3, 1 by 3, then 2 plus minus 2 by 3. 2 minus 2 by 3, that is 6 minus 2 by 3, that is 4 by 3. And R2, here the element is 3, then R2 changes as R2 minus 3 times R3. R2 minus 3 times R3, that is 3 minus 3 times 1, this will become 0. The value of x4 changed as, earlier it was 4 minus 3 times 1 by 3, that is 4 minus 1, it will become 3. And the other values, 0 minus 3 times 0, 0, then 0 minus 3 times 0, 0, again 1 minus 3 times 0, it is 1, then 0 is here, 0 minus 3 times 1 by 3, that is 0 minus 1, that is minus 1, then minus 1 minus 3 times minus 2 by 3, that is minus 1 plus 2, this will become plus 1. And in the last row, it is here minus 1, so R4 changed as R4 plus R3. Then when R4 plus minus 1 plus 1, this will become 0. Then value is, here it is 2, actually 2 plus 1 by 3, that is 2 plus 1 by 3, that is 7 by 3 will be the new value of x2. Then this value, that is 1 plus 0, 1, 0 plus 0, 0, 0 plus 0, 0, then 0 plus 1 by 3, 1 by 3, then 1 plus minus 2 by 3, 1 minus 2 by 3, that is 3 minus 2 by 3, that is 1 by 3. So, our solution changed as x1 1 by 3, x2 7 by 3, new solution is 1 by 3, 7 by 3, x3 19 by 3, x4 3, x5 0, x6 0. This is the new solution to our problem. So, corresponding to this new solution, you want to check what is the value of f of x and what are the values of the net evaluations. So, f of x is equal to 19 by 3 into 0 plus 3 into 0 plus 4 into 1 by 3 plus 5 into 7 by 3, that is 4 into 1 by 3 plus 5 into 7 by 3. That is the new value of the objective function, that is 4 by 3 plus 35 divided by 3, that is 39 divided by 3. We are getting the objective function, that is 39 divided by 3, or it is just 13. So, some more increased. Objective function attained the value 13. Now, we want to check whether this is the end of the solution or this is the optimal solution, or we want to do the iteration again, or we want to move for further step. So, that is determined by decided by the net evaluation Zj minus Cj values to calculate Zj minus Cj. So, here 0 into 0, 0 into 0, 1, 4 into 1, 4 plus 0 into 5, 5, that is 4 minus 4, it is here 0. Then for the next basic variable also net evaluation will become 0. Then x3 net evaluation will become 0, x4 also net evaluation will become 0. So, for all the basic variables net evaluation will become 0. For other non-basic variable, they are now x5 and x6. So, for this x5, 1 by 3 into 0, minus 1 into 0, 4 into 1 by 3 plus 5 into 1 by 3 minus the cost, that is 0. So, this is the net evaluation, that is 4 by 3 plus 5 by 3, that is 9 by 3 minus 0, that is 3 minus 0, we are getting 3 here. And for the next x6, 4 by 3 into 0 plus 1 into 0 plus minus 4 into minus 2 by 3 plus 5 into 1 by 3, that is minus 8 by 3 plus 5 by 3, that is minus 3 by 3, that is equal to minus 1. So, we are getting here minus 1. Again, this is not the final step for the problem, because here this Z6 minus C6, that is minus 1. So, all the Zj minus Cj values are not greater than or equal to 0. So, this is again not an optimal solution for our problem, that is we want to make some more iteration. Here this is the incoming variable, x is incoming variable. So, to decide the outgoing variable, that is again the ratio. So, as before here 6 divided by minus 1. So, here 19 by 3 divided by 4 by 3, then 3 divided by 1, then 1 by 3 divided by minus 2 by 3, and 7 by 3 divided by 1 by 3. So, here this is 19 by 4, this is 3, this is negative, this is 7. So, here among this ratio the least positive, we want to identify the least positive is 3. So, this is the outgoing variable. So, when we are considering this outgoing variable and incoming variable, this is the pivotal element, one is the pivotal element. So, pivotal element already it is 1. So, we want to make no change, but the change that has to made is we want to change all other elements of this column, that is last column, make it to change them as 0. So, such that type of row transformation has to be done. So, the next table comes as 4, 5, 0, 0, 0 and 0. Now, x3 here, but x6 comes and x4 goes out. So, here x6, then x2 and x1. Now, these are the basic variables. Their cost 0, 0, 5 x for x2, it is x, here it is x1 and here it is x2. The cost of x1 is 4 and cost of x2 is 5. Now, the row vector, here already the pivotal element is 1. So, there is no change, the value of x3, x6 becomes 3 and other elements 0, 0, 0, 1, minus 1 and 1. We want to make all other elements of the last column as 0. So, that type of change has to be done for all other rows. So, first row R1 changed as R1. Here it is 4 by 3, 4 by 3, R1 minus 4 by 3 into R2. R1 minus 4 by 3 minus 4 by 3 into 1, this will become 0. So, the changes on other points, that is here it is 19 divided by 3, 19 divided by 3 minus 4 by 3 into 3. That is 19 by 3 minus 4, that is 19 minus 12 all divided by 3, that is 7 divided by 3. So, this will become 7 divided by 3. Now, the first element, that is here 0, 0 minus 4 by 3 into 0, 0. Here it is again 0, 0 minus 4 by 3 into 0, 0. Then 1. 1 minus 4 by 3 into 0, 1. Next 0. 0 minus 4 by 3 into 1, that is minus 4 by 3. Then 1 by 3 minus 4 by 3 into minus 1, that is 1 by 3 plus 4 by 3, or it is 5 by 3. Here it is 5 by 3. So, that is the change happened in the first row. Then second row R2. Okay, R2 is the row of our basic variable. So, R3 new basic variable. So, R3 here it is minus 2 by 3, this has to be changed as 0. So, you can make this change, R3 implies R3 plus 2 by 3 into R2. that is minus 2 by 3 plus 2 by 3 into 1. This will become 0 here. Now, the value of x1, it is 1 by 3. So, it is changed to 1 by 3 plus 2 by 3 into this 3, that is 1 by 3 plus 2, that is 3 into 6 plus 1, 7 divided by 3. So, again we are getting 7 divided by 3 here, and this all other elements 1 plus 2 by 3 into 0, 1 plus 2 by 3 into 0, that is 1, 0 plus 2 by 3 into 0, that is 0, then next 0 plus 2 by 3 into 0, that is 0, 0 plus 2 by 3 into 1, that is 2 by 3, then 1 by 3 plus 2 by 3 into minus 1, 1 by 3 plus 2 by 3 into minus 1, that is 1 by 3 minus 2 by 3, that is minus 1 by 3. Let us see. Similarly, you want to change the fourth row also. Fourth row R4 implies R4, the element is 1 by 3 here. So, this minus 1 by 3 times R2, that is R4 implies R4 minus 1 by 3 times R2, that is 1 by 3 minus 1 by 3 into 1, the element will be becoming 0. Then the value of x2, that is here 7 by 3. So, that is changed to 7 by 3 minus 1 by 3 into 3, that is 7 by 3 minus 1, that is 7 minus 3, 4 divided by 3, changes as 4 divided by 3. Now, we want to change all other elements of that row. So, 0 minus 1 by 3 into 0, 0, then 1 minus 1 by 3 into 0, that is 1, 0 minus 1 by 3 into 0, that is 0, then next 1 by 0 minus 1 by 3 into 1, that is minus 1 by 3. Now, the value comes here, that is 1 by 3 minus 1 by 3 into minus 1, that is 1 by 3 plus 1 by 3, that is 2 by 3 comes here. Now, the solution, basic feasible solution of our problem, the basic variables are x1, x2, x3 and x6. Corresponding solution x1, that is 7 by 3, x2 4 by 3, x3 7 by 3, x4 0, x5 0, x6 3. This is a new basic feasible solution. You want to check whether it is an optimal solution. For that, again we want to calculate the net evaluation Zj minus Cj values for all the variables. Now, it is before what we want to know what is the value for our objective function corresponding to this solution. So, the objective function f of x, that is equal to 7 by 3 into 0 plus 3 into 0 plus 7 by 3 into 4, that is 28 by 3 plus 5 into 4 by 3, that is 20 by 3, that is 48 by 3, that is equal to 16. So, we got the value of f of x, that is equal to 16, some more improved. In last case it was last step it was 13, now it is equal to 16, f of x is improved. Now, it is to test whether all the Zj minus Cj values are greater than or equal to 0, that means whether this is the optimal solution for our problem. So, calculate Z1 minus C1, 0 into 0, 0 into 0. So, it is equal to 0 because x1 is the basic variable. Similarly, x2 is also basic variable. So, it is 0. Net evaluation for x3 is also 0 because x3 is the basic variable. So, x6 that also 0. But for x4 to calculate, minus 4 by 3 into 0, plus 1 into 0, plus 2 by 3 into 4, that is 8 by 3, plus 5 into minus 1 by 3, that is 8 by 3 minus 5 by 3, that is equal to 3 by 3, that is equal to 1. So, we are getting here 1. Then for the next variable, that is x5, the next evaluation is to be calculated. 5 by 3 into 0 plus minus 1 into 0 plus 4 into minus 1 by 3, that is minus 4 by 3 plus 2 by 3 into 5, that is 10 by 3. So, that is equal to plus 6 divided by 3, that is equal to 2. So, we are reaching an end because all the net evaluations are greater than or equal to 0. So, 0, 0, 0, 1, 2 and 0, all the net evaluations are greater than or equal to, all the Zj minus Cj values are greater than or equal to 0 in this step. So, our iteration stops here. We got an optimal solution for our problem. The optimal solution is x1 is equal to 7 by 3, x2 is equal to 4 by 3 and x3 that we don't want to consider because x3, x4, x5 and x6 are our slack variables, that is just introduced for making them inequality to an equality. So, our actual variables are x1 and x2, their values are 7 by 3 and 4 by 3 and our objective function f of x is equal to 4x1 plus 5x2. Based on this variable, the value of our objective function that is equal to 16. So, the maximum value of f of x equal to 16, where x1 is equal to 7 by 3 and x2 equal to 4 by 3. That is the solution of this the given linear programming problem by the method of or by Simplex method. So, here the Simplex algorithm. In short, the Simplex algorithm can be stated as follows. Step 1, make the LPP in maximization type. 2, in standard form of the LPP, ensure BAs are non-negative or make them as non-negative. 3, obtain the initial basic feasible solution. 4, form the Simplex table. 5, calculate net evaluation Zj minus Cj for each variable j. Zj minus Cj, that is Cb into Yj minus Cj. If all Zj minus Cj's are non-negative, the solution is optimal. If that is not the case, improve the solution by finding the new basic variable by noting the most negative, least positive net noting the most negative net evaluation, that is the most negative value of Zj minus Cj. Let it be for the variable xr. Determine the determine xr as the or consider xr as the incoming variable and next to determine the outgoing variable. So, we are considering the ratio, among the ratio we are considering the least positive. For which variable the least positive ratio comes, that variable goes out, and if xr is the variable is having the most negative net evaluation, that is coming in. Then if all yi are less than or equal to 0 for I equal to 1 to etc. m, then there is an unbounded solution to the given problem. Then next form the Simplex table with the revised basis. Again we are repeating the steps and finally we are achieving the case where all the Zj minus Cj values are greater than or equal to 0 as we illustrated in the last case, and we are getting the optimal solution for our linear programming problem. Next is degeneracy. In Simplex method, the minimum value among the set of non-negative ratios decides the outgoing variable at a particular iteration. In some iteration, the minimum non-negative ratio may happen for 2 or more basic variables. In that case, a tie occurs as to which variable is to drop. One can arbitrarily decide in favor of one, but then it turns out that the variables which tied with it and continue to remain in the basis also become 0. In other words, one or more of the basic variables to have 0 value. Such a case is called degenerate. In degeneracy, theoretically the basis has been changed, but the value of the objective function remains the same. Geometrically, it may be interpreted as the case of two coincident vertices. We change from one to other vertex, but substantially remain where we are. In most cases, we go ahead with our iterations and finally reach a basis with improved value for the objective function and finally get the optimal solution. But in some cases, after much iteration, we arrive back at the degenerate basis from which we started. Such cases are termed as cyclic degeneracy. Now, we are going to some problems. problem 1, maximize f of x equal to f of x is equal to 107 x 1 plus x 2 plus 2 x 3 subject to the constraints 14 x 1 plus x 2 minus 6 x 3 plus 3 x 4 equal to 7 and 16 x 1 plus 1 by 2 x 2 minus 6 x 3 less than or equal to 5, 3 x 1 minus x 2 minus x 3 less than or equal to 0, where x 1 greater than or equal to 0, x 2 greater than or equal to 0, x 3 greater than or equal to 0, and finally x 4 also greater than or equal to 0. So, here again we want to introduce some slack variables, they are x 5 and x 6 to the problem. The constraints are becoming equalities as follows. That is, the third and fourth constraints are inequality type. So, we are adding the slack variable x 5 to the second and x 6 to the third inequality, and they are becoming equality as minus 6 x 3 plus x 5 equal to 5, then minus x 3 plus x 6 equal to 0. Here, when we are trying to solve this problem by the method of simplex, we get all the negative valuations Zj minus Cj as negative values, but the column vector corresponds to the most negative valuation will contain no positive elements. Hence, the corresponding column vector cannot enter the basis. So, this is the case. This is an indication that there is an unbounded solution to the given linear programming problem. So, as we discussed in the last narration or illustration, we can solve all the linear programming problem by simplex method. In some cases of unbounded solution and some situations are arises. So, in that situation we want to move for further higher steps. Next, we are considering the problem LPP of minimizing f of x, that is equal to minus 5 x 1 minus 3 x 2 subject to the restrictions x 1 plus x 2 less than or equal to 9, x 1 plus 2 x 2 less than or equal to 18, x 1 less than or equal to 4, x 2 less than or equal to 3, and non-negativity restrictions x 1 greater than or equal to 0, x 2 greater than or equal to 0. So, here our given problem is to minimize f of x, that is equal to minus 5 x 1 minus 3 x 2. So, in the first step we are changing the problem to maximization problem, that is to maximize minus f of x. Minimizing f of x means maximizing minus of, let it be phi of x, that is equal to minus 5 x 1 into minus, that is 5 x 1 plus 3 x 2. So, the problem changed to maximize 5 x 1 plus 3 x 2 subject to the constraints x 1 plus x 2 less than or equal to 9, x 1 plus 2 x 2 less than or equal to 18, x 1 less than or equal to 4, x 2 less than or equal to 3. So, in this case we want to change the inequality restrictions as equality by introducing some slack variables. Let x 3, x 4 and x 5 are the slack variables considered, then x 1 plus x 2 plus x 3 equal to 9 is the first restriction, then x 1 plus 2 x 2 plus x 4 equal to 18, that is the next restriction, then x 1 plus x 5 equal to 4, that is the fourth equation. Then one more slack variables to be added here, x 2 less than or equal to 3, that is x 2 plus x 6 is equal to 3, and x 1, x 2, x 3, x 4, x 5 and x 6 all are greater than or equal to 0. So, our problem changed it into standard form, that is maximize 5 x 1 plus 3 x 2 plus 0 x3 plus 0 x4 plus 0 x5 plus 0 x6 subject to the restrictions, that is x1 plus x2 plus x3 that is equal to 9, then x1 plus 2 x2 plus x4 equal to 18, x1 plus x5 equal to 4 and x2 plus x6 equal to 3. Now, we can consider these x4, x3, x4 and x5, x6 as the basic variables and substitute x1 and x2 as 0 as we already considered in the illustration. Then we will get the initial basic feasible solution, basic feasible solution, because we will get x3 equal to 9, x4 equal to 18, x5 equal to 4 and x6 equal to 3, and x1 and x2 are 0, all are greater than or equal to 0. So, that is the initial basic feasible solution. As before, we will test what is the value of f of x for that initial basic feasible solution. The value of f of x or phi of x, here it is 5 into 0 plus 3 into 0, it will be 0. Then the next step, we want to check whether this solution is optimal or not. For that, we will calculate the Zj minus Cj values. So, in this case, the Zj minus Cj values are not all greater than or equal to 0 in the first iteration. Then the first variable, that is like x1 will come in and the solution will improve, and finally, we are doing the iterations, different steps until all the Zj minus Cj values are greater than or equal to 0. In that step, we can stop the iteration and the value of f of x for that particular solution as the optimal solution of the problem. In this problem, this will become the optimal value of f of x, that is the maximum value of phi of x is equal to 29 for some Zj minus Cj values, or we can you can just verify whether it is correct or not. Finally, we will get the maximum value of phi of x after many iteration, it will become 29, subject to the variable values x1 equal to 4, x2 equal to 3. When x1 is 4, it is 20, when x2 is equal to 3, it is 9, 29. This will be the final answer, x1 equal to 4 and x2 equal to 3, and maximum value of phi of x is equal to 29. So, this implies the minimum value of f of x is equal to minus 29 for the value of x1 is equal to 4 and x2 equal to 3. So, you can just verify this answer by doing some more iterations and by drawing the Simplex table. So, we can conclude here, and in the next class we will go to the bigger method and artificial variable technique for solving some linear programming problem. Hope you enjoyed this session. See you next time. Until then, goodbye.